Get started. Okay, let's get started. My pleasure to introduce today's speaker, Professor Aaron Frank. Paragraphs from your webpage. Dr. Frank comes to us from postdoctoral studies as a prestigious presidential postdoctoral fellow at the University of Michigan, where he worked on developing a framework for modeling the structure of small non-coding RNA molecules. Aaron carried out undergraduate studies at City University of New York, majoring in chemistry. He completed his PhD in physical chemistry from UC Irvine and worked as a research fellow for 2 years prior to moving to Michigan as a postdoctoral scholar at
Namiram,
a pharmaceutical company directed towards drug development for RNA targets. Professor Frank's research in biophysics will focus on development of integrated approaches to elucidate the ensembles of conformation in small non-coding RNA molecules that are of growing importance as potential targets for cellular controlled function. His research will employ both experimental techniques of nucleic acid and computational biophysics, combining key approaches for characterizing the structure and motions of flexible molecules. Welcome, Aaron.
Thank you. Okay, so first of all, thank you for taking the time out to come to listen to me talk about some of the work that we're doing in my group. And so today what I'll talk about is, let me make sure I have the pointer, some of our solutions, data-driven solutions to challenges that we face in biophysics. So to start off, I'll just first do something that I typically forget to do, which is acknowledge the people who do a lot of the work, or who I collaborate with, I should say. So I have my group members here. So a lot of the work that I'm going to talk about has been carried out by Keshan, who is she's a graduate student who will be leaving the group soon. If I have time, I'll talk about some of the work that Indrajit has done as well. So this is the group, the graduate students, and also some of my collaborators. My collaborators are the ones that motivate a lot of things that we do, right? And so I'll try to bring that to the fore as I go through this presentation. So a pretty intimate group, so if you have questions about something that I said that wasn't clear, feel free to stop me and ask questions along the way. Okay, so a good starting point for the research that we do is the central dogma of molecular biology. You've probably seen this many times, but I'll quickly go through this, right? So the idea is that, all of the information needed to sustain life is stored in our genome in the form of DNA. That DNA is transcribed to form RNA, which is then translated to produce proteins. So a lot of the focus in terms of biophysics and in general has been on focusing on proteins, right? But the question is, what fraction of all the RNA transcripts that are translated actually are translated into proteins? And the answer is a very small fraction. If you actually look at the numbers, right, 93% of the genome codes for some RNA transcript, yet only approximately 2% of the genome codes for proteins. So when I took biochemistry in undergrad, the idea was that all of the 98% of the information stored in the genes is just junk, right? But now we know that's not the case, right? And it turns out that a lot of the RNA that do not necessarily code for proteins actually have functional relevance. And so it brings this point, which is drug discovery has been focused mostly on proteins, but what about RNA, right? If indeed RNA is able to regulate key processes, biological processes, we might actually want to also focus on RNA as a drug target. So there's a lot of excitement right now about targeting RNA and treating them as a drug target, and some of that motivates some of the research that we do. So if I had to break down the research in my group, it's a focus in four main areas, right? So we do a lot of work centered around structure prediction, that is predicting the structure of an RNA. So typically what we find ourselves in the situation where we can use a variety of computational tools to generate a lot of structures for a given RNA. The problem becomes the selection problem. How do you select from all of these diverse set of structures the one that we would use as our prediction, right? And so we've actually employed a technique where we use chemical shifts that you can get access to from NMR experiments to be able to help us do this selection. So once we have structure of an RNA target, the next thing we're interested in is try to find small molecules that might be able to bind to that structure and stabilize a particular conformation. And so here what we're trying to do is to find small molecules that fit neatly into some binding pocket. And so here you're seeing an example where we've docked a series of small molecules into this RNA. And the idea is that based on the docking score we get, which is should give us some sense of whether or not this small molecule can favorably interact with the RNA, then we could probably prioritize those molecules and test them experimentally. Something that we're starting to do a lot of now is molecular design. And so right now we're developing techniques where we can design small molecules that bind to a particular RNA at a particular location, or biomolecules in general. And the way we do that is by leveraging generative models, right? So I know most of you are probably well aware of the excitement around generative models. And so there are lots of interest in using generative models to design small molecules. Now what we're doing is actually interfacing these generative models with molecular docking simulations so that we can actually sample structures from these latent space described by these designers, dock them, figure out if they bind neatly. If they do, send them back to the space, change the molecules slightly, and do this in an iterative process, and it allows us to design novel molecules. Now, one of the challenges, if you pay attention, you realize one of the challenges in this field is the fact that some of the molecules you design are not chemically feasible, right? So you see some of these molecules look quite strange, right? So there's a lot of work being done around generating or building generative models that can output realistic molecules. But that's not the focus of what we're doing. Our work is mostly taking these generative models and then using them in a design process. The last area that we're interested in is what are called accelerated simulation methods. And these methods allow us to simulate very complex processes. So this was supposed to be a movie, but it's not working. But essentially what we're interested in is processes like the unbinding of a ligand from a target or the dissociation of a complex. So using conventional molecular dynamics simulations, these processes take a very long time to observe. So one of the things we're doing is coming up with clever ways to accelerate these processes so that we can observe them in a given amount of simulation time. What I'll do today is probably talk mostly about structure prediction work, and if we have some time, I'll probably talk about some of our accelerated simulation methods. So we're a computational biophysics group, or biophysical chemistry group, and so the work we do centers around or the interface of physics, biology, and chemistry. Now, there's an additional domain, and that domain is the domain of data science, right? And so we sit right at this interface where we try to leverage developments in data science to help us answer questions that lie on this interface here. So the first thing I'll talk about is tools to predict RNA secondary structure and also 3D structure, the tertiary structure. And all of that is motivated by this problem, right? So for a given RNA, you may know the sequence. And so you want to figure out what the structure of that RNA is. And so this could be broken up into two separate processes. The first is predicting what the secondary structure is. And because you will see this a number of times in the talk, I just want to orient you. So this is the sequence, and this is the 5' end and the 3' end. And everywhere you see a line connecting two nucleotides corresponds to the base pair, right? So in this case, this G is base pair to this C here. And this U base pair to this A here. So once you have the secondary structure, you can build models that are consistent with the secondary structure, right? So the workflow for going from sequence to structure will be to first predict the secondary structure. Once you have secondary structure, use that to generate models that are consistent. And so there are lots of tools that already exist to carry out this process. And so we're going to focus here mostly on this first step, which is to predict secondary structure from sequence. So the way we're going to do this is using an integrative approach where we leverage information from NMR spectroscopy, right? And the reason we want to do this is kind of illustrated here. So imagine we have this RNA. This is a sequence, and it turns out that RNA molecules can adopt multiple conformations. And so it's not a one-to-one problem. So a single sequence could map to many metastable RNA conformations. And so here is a hypothetical example where this sequence can fold into these two structures. And so one, you have what we will call the ground state. That's the state that has the highest probability of being observed. And then there's this transient state here. So conventional methods for determining the structure, if you applied it to this hypothetical scenario, right, would only be able to access or would only get signal from this dominant state. So essentially what it means is that its transient state is going to remain invisible to these techniques. And that's because of the fact that it's so lowly populated. Well, never mind. So there's a problem here, but that's fine. So the point now is that there are these techniques, NMR techniques, that actually allow you to detect the chemical shift signature for this transient state, right? And what that in principle allows us to do, if we have the right methods, is probably take this chemical shift information for the transient state and actually try to model the structure, right? So what we're going to try to answer here is, can we use this chemical shift to conditionally predict the secondary structure of an RNA? And say conditionally because we're conditioning the prediction. We want to attempt to condition our prediction of structure based on chemical shifts. So if we have chemical shifts for these two states, we want to actually be able to make two distinct predictions about the secondary structure. And that is going to be driven by the chemical shift. So we approached this using a machine learning approach. And so what we did is to collect a set of NMR structures. So we know what the structures of the RNA is, or the RNAs are. And we have chemical shift data. So we do some data, some quality control steps to then produce a set of high-quality NMR structures and chemical shifts where we try to mitigate any error that is in the data. And once we have this structure chemical shift database, we trained these machine learning models that attempt to predict the base pairing status of every residue in the RNA based on the chemical shifts, right? Now, when I say base pairing status, I'm just saying for a given residue, we ask the question, is this residue base paired or not? We're not asking if what this residue is base paired to. That's another question that we'll get to that in a bit. So this will be the workflow. You get the data, then train these models, and this model will then be used to predict the base pairing status. And then we have some model assessment steps. So the technique we use to actually train the kind of classifiers we use were these neural network classifiers. In this audience, I don't think I have to spend a lot of time describing how neural networks work. But for us, we feed in the input layer chemical shifts. And again, this is the chemical shift for all the atoms in a given residue that have an NMR assigned to them, right? And then we feed this into this network, and at the end, it predicts whether or not that residue is base paired. So chemical shifts for residue goes in, the output is a probability that that residue is base paired or not. So in our approach, we generated 6 independent, what we call CS to BPS classifiers, meaning chemical shift to base pair status classifiers. And we trained this on 108 RNA structures, for which we also had the chemical shift data. And so here are some of the results. So reported here, we're showing the true positive rate. That's the probability that if we predict a residue to be base paired, that is in fact base paired. And you can see our mean true positive rate is about 0.95, which is acceptable. And the true negative rate is about 0.72, right? So you can see there's a clear difference between the true positive rate and true negative rate. And the reason for the lower true negative rate, we believe, is that we have less examples of residues that are not base paired in our data set, right? So there is an imbalance in our data set. And I think it's reflected in the lower performance in terms of predicting whether or not a residue is not base paired.
Aaron, I want to
Question?
ask a more basic question. If you have carbons or hydrogens individually labeled,
Yes.
not multiple ones individually labeled.
So for every residue, right, you have multiple sites we have chemical shifts in multiple sites in that residue.
Right. If there are 5 carbons labeled one at a time,
Right.
So
So there, it is possible to do site-specific labeling, right? But if you do site-specific labeling, you might essentially be able to assign the chemical shifts for a given residue. So you are able to get access to the set of chemical shifts for those carbons or protons.
then chemical shift really means the time for the formation function, time of relaxation.
Yeah, which is then converted into this measure that gives you a sense of the electronic environment around the particular site.
Formation is not just in an ending state, but how fast it moves. Yeah.
Right. So I think there is some in the chemical shift itself, you may not have that measure of this relaxation process you're talking about, right? But you can definitely acquire that information from NMR, right? Oh, yeah. Question?
Much better will compared to only predicted by RNA structure MO.
So this is a good question. So the way we answer this question is that that's not what we're interested in, because the challenge here is to take a single sequence and make multiple predictions. If you feed your sequence into M4, for example, you typically get one answer, right? And that's the global free.
So if you get to the most dominant active state, what is the difference?
Yes, so the difference in accuracy is probably we're better by about 0.02, right? So it's not significant, right? But that's the point I'm trying to make. We're not concerned with that, because what we're after is an ability to condition our prediction on the chemical shift data, right? So in cases where you have an RNA that can adopt multiple states, and let's say one of the states is a minor state, right? We want to actually be able to take the chemical shifts associated with this minor state and make a prediction about what it looks like. You can't do that using these techniques where you just simply take a sequence and it gives you one prediction as to what the secondary structure is. Make sense? That's a good question. Okay, so here what we're predicting is base pairing status, but what we're after is really secondary structure, right? So we're missing that connectivity information, right? So base pairing status tells us nothing about base pair connectivity. So what we had to come up with is an approach that allows us to now turn this information about the base pairing status of individual residues into connectivity information. And so what we do, imagine you have the chemical shifts in a sequence of some RNA. You don't know what the structure is. You would feed it into a classifier. For every residue, it would give you the base pairing status, right? And we call this PIs. And then what we do is leverage the infrastructure that has already been used to incorporate these kinds of probabilities that were derived from chemical mapping data into secondary structure prediction, right? So we just feed it all probabilities, and then we add this restraint term that allows us to ensure that the structures we generate are in agreement with our predictions, and then we're able to produce a final model, right? And the cool thing about this is that we can actually utilize these predictions with most prediction methods, folding programs, because a lot of them have features that allow you to take chemical mapping information, which is just essentially gives you a measure of the probability that the residue is base paired, right? So at this stage, from this point on, there's really no difference between our approach and the chemical mapping information. The difference comes with how we arrive at these probabilities. So the question is, okay, how do we perform, right? So what we did is for all of the RNAs in our data set, which is 108, we folded the structures using our what we call CS fold for chemical shift fold. And here what you're seeing, we're reporting the true positive rate and the positive predicted value, and here we're focused on base pairs now, actual base pairs, right? So the true positive rate gives a measure of whether the probability that a base pair that is known to be base paired the probability that a base pair we predict to be base paired is actually base paired in the correct structure. And then the positive predictive rate has to do with whether or not all of the base pairs we predict it turns out to be actually true base pairs. So these numbers, what you want them to be as close as possible to 1. So you can see here we have a mean value of over 0.96, and here we have one of over 0.95. So we're happy with this result, but again, this is not what we're after necessarily, to just simply have high true positive rate and high true positive rate and high positive predictive values. What we're really after is being able to conditionally predict the secondary structure. And so what I'll show you now is an example of a RNA which this RNA adopts 2 different states, right, under 2 different sets of conditions. So this is a fluoride-ribose switch. I'm not going to talk much about what the fluoride-ribose switch does, but this is the secondary structure of the fluoride-ribose switch when it's in this magnesium-free state. And then this is the structure when it's in the apo state, and this is when you add magnesium, but not the fluoride ligand that it binds, right? So you can see a dramatic change in structure. So you see the formation of these pseudoknot base pairs that are absent in this state here. So we have chemical shifts for both states, right? And so what we did is to actually try to predict the secondary structure. And so the way to read these images is that if you see green lines, that corresponds to cases where the base pair is present in both our predicted structure and the actual structure. So these green connections here correspond to base pairs we got correct. These dotted red line corresponds to base pairs that are extraneous to our prediction, so meaning that it's present only in our predicted structure, absent in the actual structure. So you can see one of them showing up in this structure here. And so with that, you can see that we're actually able to conditionally predict the structure of this fluoride-ribose switch. And the only difference is the chemical shift that we use to get the base pairing probabilities, which we then use to guide the folding algorithm. And so in this case, the true positive rate is about 1, and then the positive predictive value is 0.98. So this is the magnesium-free state. And then for the apo state, the true positive rate is about 0.93, and the same value for the positive predictive value, right? So this is really cool. This is further. We were even more excited about this result because of the fact that here we only used data for the Gs, the guanines, right? Furthermore, we only used data for a subset of the atoms. So for H1 prime, C1 prime, H1 prime, and C8H8, right? So even with a set of sparse restraints, essentially, we're able to conditionally predict the structure, right? Any questions?
Here you do a 2-step approach.
Yep.
First, at residual level, what are the pairs? What are those that could pair, and then you fold. So is there a difficulty to directly predict which residual pairs and form base pair?
So you're asking, what about directly predicting the base pair rather than going through this process? I can imagine one could come up with an approach to do this, right? But for us, we were inspired by existing frameworks for utilizing chemical mapping data, right? And so there you do the chemical mapping experiments, they give you these probabilities, and you feed them into the folding algorithms, right? So what we did here is say, okay, what about getting those probabilities from NMR chemical shifts? And so we just kind of plugged into an existing framework to be able to predict the secondary structure. But one could definitely, for example, build models where you give it the sequence and train them to predict the base pairing directly. But that's not something we did here. Now we have a project where we're actually going the opposite direction, where we're doing RNA design, where we try to predict the sequence that maps onto a given target structure. So imagine here if you removed all of the identities of every residue here, and you asked, given this structure, can I predict what sequence would map onto it? We're doing that kind of work, and the approach we're utilizing for that work can actually be used as well for the conventional structure prediction approach, which would be what you're talking about, going from sequence directly to structure. But that's not something that we've tried as yet. Any other questions? So I guess the takeaway is that we can use TS-fold to conditionally predict the secondary structure of the Florida riboswitch. And this is very careful, right? We've tested it on 2 RNAs, and we've gotten decent results on 2 RNAs. But we still need to test this more extensively to ensure that it's something that's general, and this statement is general. So another thing we can do, there's another approach we can take to actually try to model the secondary structure of RNAs. And so imagine you can take sequence and generate several secondary structure models. And so here what we're showing are different secondary structure models. We also included the information that allows you to figure out how accurate the model is. So where you see the green lines again, these correspond to base pairs that are present in the actual structure and this particular model. The red lines are extraneous to the model. The black ones are base pairs that are missing from the model that should be there, right? So you can see you have this model here is the one that will be correct, right? This is a secondary structure model that will be correct. And then the others have some errors in them. This one here, the terminal base pair is missing, for example. So imagine you have some tool that allows you to sample these, right? One way you could incorporate chemical shifts into this analysis is by building tools to predict chemical shifts directly from these models, right? So we've actually developed a machine learning model using random forest that allows us to, for every residue, predict the chemical shifts based on the structural information that you can derive from this model here. And so what you could do then is take that chemical shifts you predict for every residue and compare them to the actual chemical shift that you have. And so one way to incorporate this is using a probabilistic approach where what you do is to essentially assign weights to every structure such that the ensemble average chemical shift matches the measured chemical shifts. And so these weights are essentially optimally assigned so that you maximize the agreement. And if you use a Bayesian framework to do that, to do this. And so you can see if you apply this to this hypothetical case, right? You have these 1, 2, 3, 4 models that have some appreciable probability attached to them, and then you have these that have 0 probabilities, right? So what you could do is then construct an ensemble that is based on these sets of structures, and you have weights assigned to them. And so the takeaway here is that we can use the chemical shifts to generate a kind of probabilistic model of the RNA structure. So rather than having a single structure, we can actually have a set of structures, and for every structure we assign a weight. And the weight here is optimally assigned by comparing the measured and predicted chemical shifts. Now, something I'm glossing over is the fact that to be able to do this, you must be able to predict the chemical shifts from these low resolution models. And so we've actually built tools that allow us to do this as well.
So Aaron, this probability can also be assigned different parts of the structure, such as you have disordered domain or floppy.
So we haven't attempted to do that as well. But one thing that there was a slide that I took out here is what one could imagine doing is actually building a consensus secondary structure model based on all of these, where you could essentially, for every base pair that shows up, you could add the probabilities across these, and then at the end, generate a single model that's composed of only the most probable base pairs, right? So it's kind of related to what you're talking about, but it's not exactly the same. But yeah, that's something that we're actually in the process of doing, and I actually took out a slide that kind of highlighted how one could do that as well. Any other questions at this stage? So one could imagine doing this at a 3D level, right? So you have this scenario here where what I'm showing you is a fragment of an RNA, that the correct structure is shown in white, and the different models are shown in green, right? And below we show the structural agreement between them, right? We get the RMSD. So these two models are the closest to the actual structure. So and then you have these models that have high that are far away from the solved structure. And so this is the kind of result that you typically encounter when you try to use modeling tools to, well, you use computational tools to generate models for an RNA, right, where you have to select among these. And so again, what you could do is compute chemical shifts from your structures and compare them to experiments and attach weights to each one of the structures. And if you do this, in this case, you could see that you can actually isolate the two models that actually have the best structural agreement with the known RNA, with the known structure, which is an NMR structure. And so it suggests that we might also be able to use this kind of probabilistic approach to model the 3D structure of RNA, right? So let's shift gears just a little bit, and we're going to talk about RNA structure prediction, but focused on RNA ligand complexes, right? So this is motivated by our interest in doing virtual screening, where we have a structure of the RNA, and we want to find small molecules that fit neatly into a binding pocket. And so the setting, the way this is typically used, you would dock, let's say, 1 million compounds into the binding pocket. For each one of them, you have to predict the pose, and based on the predicted pose, you estimate the binding affinity, and then you rank 1 million compounds based on their binding affinity and choose the ones that are predicted to be most favorable, right? So in that workflow, post-prediction is really important, because if your post-prediction is inaccurate, then your estimation of the binding affinity would also be inaccurate as well, right? So we have an interest in trying to improve the success rate of these post-prediction methods. So this is the typical setup. You have an RNA, and you could generate a number of poses. And so the pose is just a unique conformation and orientation of the ligand relative to the receptor, in this case, the RNA. And so you have some poses here, you have some poses here. You also have poses in the native binding pocket, and you have the native structure here. So this is another selection problem, right? We could generate lots of possible solutions, but the challenge is selecting which one's right. So this is going to highlight here the process is to isolate this native structure here. So the state-of-the-art methods actually exhibit a around 50% success rate, meaning that if you give it 100 RNA complexes where you knew what the structure of the complex was, in 50% of the cases you'll get it right, and 50% of the cases you'll get it wrong, right? And so we want to be able to actually develop tools to better distinguish these non-native or incorrect poses from the near-native poses. And so to begin this work, we had to design a way, what we call an interaction fingerprint, or what is an interaction fingerprint, that describes the interaction between our target receptor, the RNA, and the small molecule. And this is kind of highlighted here. You have the RNA, and then you have the small molecule. And so for every atom in the small molecule shown in the blue sphere, we calculate distance between that blue sphere and all the RNA atoms that surround it. And based on those distances, we could actually compute atomic fingerprint. So for every atom, we could feed that these Rij, which correspond to these yellow lines, into this equation here, and it gives us this number that gives us some information about the contacts it makes with specific atoms that surround it, right? Now for every atom in the ligand, right, we can assign specific atom types to those atoms, and so we actually separately, right, determine this atomic fingerprint for each specific atom type. And then we could come up with a molecular fingerprint where we kind of combine all this information for all of the atoms grouped based on their atom types into a fixed length vector that describes the interaction between the RNA and the small molecule.
It allows the host pocket to change shape.
So here we're not doing docking. So what we're doing is saying, okay, given a particular pose, right, can we predict whether or not that pose is a near native or non-native. And so you would do docking first, and then this will be a post-filtering type of approach. And so from the poses, you can get access to this molecular fingerprint. You feed it into some model, and it tells you based on the fingerprint whether or not that pose is native-like, right? So it's we're building classifiers to estimate the nativeness of the poses. So we use the random forest technique. I'm going to skip through all the details because I feel that most of you in this crowd probably have a sense of how this works. So essentially what we have is an ensemble of decision trees. In each tree, we feed in our features and we pass it through the tree, and at the end, we're able to get some probability of whether or not that pose is correct. So we have multiple of these, and so we average for a given set of features. We would average the result from each of the trees. So we trained our classifiers on a data set based on 80 RNA ligand complexes. For each system, we generated 600 poses, some of them native-like, some of them non-native. And here we're using the definition of native-like is anything less than 2 angstroms away from the known structure. And so we're talking about the RNA ligand complex structure. And so, we did all of this in sklearn. So I'm just going to show you a number of comparisons between the actual and predicted pose. So on the left, you have the actual pose, and then on the right, you have the predicted pose, and I'll go through them one by one. So this is a case where our classifier failed to recover a pose that was actually in the pocket. So the reason why there's nothing here is because the molecule is docked someplace else, right? So this will be an example of failure. This will be another example of failure. The actual the small molecule in the actual structure is on the surface, whereas in our structure it's kind of buried inside someplace. But for the rest, you can see pretty good agreement between the actual and predicted poses. There are cases where there might be some issues related to the orientation of the small molecule, but for the most part, we're getting the structures correct. And so here, all we've done is train these classifiers, and now what we do is feed in features based on a molecular fingerprint and output probabilities that they're native-like, and then rank that list and then identify the ones that have the highest score, and these are the ones that we call the predicted pose. And so you're seeing the results here. So one of the questions you have when you utilize these kinds of machine learning approaches is whether or not you've learned anything that might be transferable, right? This is a question that I've always, I wouldn't say struggled to answer, but kind of rebelled against, because for us, very often we have a very specific goal we're trying, a specific question that we're after, or a task. And the task in this case is just to be able to predict the structure accurately, right? So one school of thought would be, once you're able to accurately predict the structure, why care about things like transferability and interpretability, and also the doing importance analysis, right? So recently we started to actually think a little bit more about exploring our models a little bit more and trying to challenge them. And so one of the things you could imagine doing is to test transferability. You could take a related problem and try to use the classifiers to address them, right? So here is an example where we have this RNA, right? This is a fragment of an RNA from a soft NMR structure. These are these 2 residues. And we have a set of decoy structures where these residues have alternate positions, right? And so if you treat one of these residues as a ligand, right, you can actually make use of this, the framework that we've used to predict RNA small molecule poses to actually try to resolve these decoys here. And so what we did is, for these residues, we treated each as a ligand, passed it through the same classifiers that were trained on only RNA small molecule data. And at the end, for every structure, we get a score, and we asked whether or not the structures that have the highest score are actually the correct structures, and the ones that have the lowest scores are the incorrect structures. So what you can see arranged is the structures that have the highest classification scores. So the top 5, and then the bottom, the bottom 5. And we had about 100 of these structures. And so you could see for the structures that have the low classification scores, there are clear disagreement between the actual and predicted structure. So this is an example where we've trained this model only exclusively on RNA small molecule data, and we've tried to extend it to a related problem, right? And to do that, we had to simply treat each residue individually as a ligand, and then use the same infrastructure we use for classifying RNA ligand poses. So this is something we're actually now trying for proteins, right? So we could take every residue in a protein, treat it as a ligand, right? And then classify that residue in an RNA protein complex. The challenge is how exactly do we combine these probabilities for a protein that has multiple residues, right? One approach would be to treat them as independent, right? Where the probabilities you can treat them as being dependent, right? So we haven't figured out exactly how to combine that as well, but it's kind of interesting that we were able to actually extend this beyond the RNA small molecule problem itself. So any questions about this? So any questions about the classifiers or our approach here?
I have a question on the first part about folding predicted structure. Your approach to machine learning for patterns from
right.
How much that can be combined with this physical model, the dynamics of actual folding in silicon? Are these two complementary enough that apply both to get higher accuracy?
So, in a sense, if you look at so here we have this restraint term that depends both on the thermodynamic energy and the restraint that we're providing, right? So this is indeed a hybrid, right? That contains information about the general physics of the interactions, but also this information that we got from our chemical shifts. So tuning the strength of this restraint term relative to the thermodynamic component of the folding free energy would dictate exactly which one dominates, right? So that becomes the hyperparameter itself, which has to be optimized. But indeed, this is actually a hybrid approach.
Provided orthogonal information.
So yeah, so we haven't, because a lot of what we're doing is very problem-driven, meaning that okay, we want to predict conditionally predict the structure of an RNA. We've kind of focused on that a lot, right? But I think there are opportunities to try to improve the folding algorithms based on this kind of approach, right? Where you can probably tweak the parameters such that you are able to reproduce the results when you utilize this hybrid model. Right? Okay, so this is some of the tools that we've developed along the way. We have this CS to structure tool, which is what allows us to go from chemical shifts to secondary structure. So this encompasses what we talked about in the beginning. We also have a tool, Lamar-D, which allows us to get chemical shifts from 3D structure. And so this allows us to then compute chemical shifts from the 3D RNA structure and then compare them to experiments and be able to make some guesses as to what the structure might be. We've recently developed this tool called PyShifts, which is a PyMo plugin that allows us to analyze biomolecular ensembles based on chemical shifts. So you feed in the structure, it computes chemical shifts from the structure, projects the chemical shift error onto the structure, and you can analyze exactly where you see disagreement. So this is a tool that we think might be useful to help guide the analysis of biomolecular ensembles. It also does some clustering in chemical shift space. So essentially, you can cluster based on chemical shifts, which has the advantage of not, because the chemical shifts we utilize depend only on distances, then you don't have to worry about aligning structures to ensure that you remove this component from the clustering. And then RNA poses is the encapsulates the classifiers that I talked about that we use to study RNA ligand poses. So We're actually also working on this science gateway, working with the XC program at the NSF. And so we call it structure-based machine learning tools for RNA. And so the idea is that users would come in and upload structure, and then we would use a variety of our tools to be able to make some predictions based on structure. So this is something that's in the works. It's not yet live, but the reason I put this up here because I think for those of you who also do tool development, you might also want to consider utilizing this facility from the NSF that allows you to build these science gateways that gives users access to your tools. The cool thing about this is that they actually consult with you and they really guide you through this process, right? And so they do a lot of the heavy lifting. So if you build tools, you might want to consider using XC to help you deploy some of them. So we're going to shift gears now. We're not going to talk in the time I have remaining. We're going to talk about not data-driven approaches, but I guess physics-driven approaches. So we're going to talk about some of the tool we've developed for optimistic simulations of complex processes, biological processes, right? So unfortunately, the videos are not playing, right? So you don't get to see all of the fun videos that we created, right? But if you could, this is what you would see, right? So we have this. This is an example of this complex here, CDK2 bound to this small molecule. And here we show the residence time, right? This is the time that on average this small molecule would spend on CDK2. This is in excess of 7,000 seconds. So this is a very long timescale process. And so we, wanted to use molecular dynamics, and there are lots of interest in using molecular dynamics techniques to kind of simulate this kind of complex process. Now, so we initiated about 20 simulations. The length, each of them was about 250 nanoseconds. See the mismatch between these timescales. The wall time required for these simulations was about just over 100 hours. And we were able to observe 0 unbinding events, right? And this is a typical scenario where you have these long timescale processes and you're trying to simulate them using conventional MD simulations. So based on this residence time, right, it will take 3 by 10 to the 8 years to actually simulate this process, right? And I don't have that kind of time, right? So the reason for this mismatch is because there are these barriers that separate regions in space, right? So you have let's say you're trying to simulate the transition between these two states in this region F and this region U. The reason why the simulations don't yield unbinding events is because essentially we're stuck in this region here. And these barriers are very high relative to the terminal energy in your system. So what's happening is that all of the simulation time is spent in this region here, and you never actually see this escape to this product region. So if you ask someone, how would you solve this problem? They would say, well obviously just lower the barrier, right? And so you could actually do that, right? You could scale the potential and lower this barrier, and you could actually increase your probability of seeing these kinds of transitions. Now, if you were to do this, right, where you take your system and you do complete scaling of your potential, and your potential is just this mathematical equation that takes in your structure and outputs forces and energies, right, and which are used to propagate your dynamics using classical mechanics, you see unfolding, right? Well, you would see unfolding if the video played, right? So we don't want that, right? So one of the solutions is to actually do potential scaling where you restrain most of the region around your pocket, so in this magenta here, but you keep flexible the region where you're interested in seeing where the ligand is actually bound. And so if you do that, you can actually see unbinding events in a really, really rapidly, depending on the extent to which you lower this barrier here. Now the problem is that there can be instances where, in order for this ligand to unbind, you have to have some conformational change somewhere else, far away from the binding pocket, right? So this kind of approach would actually fail in those kind of scenarios. So what we were after were approaches that allowed us to simulate these kinds of dissociative processes where we don't have to include any kind of restraints on our system. So our approach is to do something simple. We decided that if we can make the interactions between ligand and water stronger, right, that should actually accelerate the rate of unbinding. Because what would happen is that the water would rush into the binding pocket and exchange the ligand protein contacts with ligand water contacts, and then decouple the ligand from the protein or the receptor and leave, right? Now you might ask, okay, well, yeah, that seems like an indirect approach to do this. Why not just reduce the interactions between the ligand and the protein, right? So indeed, we tried this initially, and you can imagine if you have a ligand that's really, really deep inside some buried inside a pocket, scaling the interactions will indeed decouple the protein and the small molecule, right? The problem is that the ligand becomes trapped inside of the protein, because what has to happen as well is that the protein has to open up to let the ligand out, leave as well. So by scaling up water ligand interactions, we actually do two things. One, we replace the protein ligand contacts with protein water contacts, but we progressively make the ligand bigger, and so it kind of swells and pushes open the protein and allows the ligand to leave. Right? So this is how we do the scaling. So we scale the Lennard-Jones potential, which is shown here, and this would be a case where we have the scaling parameter alpha prime, and ij corresponds to the ith atom in the ligand and the jth atom in the water. And this would be a case of the on-scale potential. And we could scale them such that we increase this well depth, which makes the interactions between the water and the ligand more favorable. And you could do this at a number of different scale values, right, where you make this well depth deeper. And so what we did, again, can't see it, but this is what you would see here is the conventional simulation of the complex, and then what we call our selectively scaled simulation, where we selectively scale the water ligand interactions. And you see this ligand actually leaves in a very short simulation time, whereas the ligand here stays inside of the receptor. And so we've published this work recently, and as a way to accelerate the unbinding. Now we've also, along with this, introduced two extrapolation techniques. Why do we need extrapolation techniques? Well, because we're accelerating time, right? Events happen faster than they normally would, right? So we have to find a way to be able to estimate what the kinetics we observe would be if we didn't scale the potential. So we have these extrapolation methods where we would run simulations at different scaling values and then extrapolate the results to the case where we don't have any scaling of the potential, and that allows us to make some estimates about the kinetics and as well the thermodynamics of the process of study. So again, this should be. So we have one of the things we wanted to, we're interested in RNA. I've shown you some protein work there, right? But this was just for developing the tools. But we wanted to apply it to an RNA. And so we had this FMN riboswitch, which is a riboswitch. Well, riboswitches are in general these RNA elements that can bind to a specific metabolite or a ligand in what's called the aptamer domain, right? And lock the RNA into this conformation that prevents it from sequestering a sequence in what's called the expression platform, right? So if we can sequester this sequence, then it prevents transcription and translation, right? In the absence of the small molecule, no sequestration of that sequence happens, and so you can have normal transcription and translation of the mRNA. And so, again, this slide didn't show up as it should, but it would kind of highlight that. So one of the things that's important when thinking about riboswitches in general is that the ability to regulate gene expression is really a complex relationship between the relative rate of folding of the aptamer domain, then the rate of ligand and dissociation, and then also the rate of transcription. Because what happens is that first you transcribe the aptamer, it folds, and then you transcribe the expression platform, right? There's this time between which you have to make this decision as to whether or not you're going to terminate the transcription or translation, right, which is dictated by the rate at which the expression platform is formed, right? So if you have a small molecule that binds to the aptamer domain and leaves very quickly, right, there's still potential for the riboswitch to make an alternate decision. So you want small molecules that stay on the aptamer domain long enough to kind of exit that decision window. So we have here I'm showing you a couple of examples of these small molecules that bind to the FMN riboswitch. You have the cognate ligand here. So this is the FMN, and this is an image of the crystal structure with a binding pocket. And then you have ribosyl, which is active, meaning that it actually is able to compete for FMN and actually inhibit the regulatory process that FMN controls, and has been shown to actually inhibit bacterial replication, right? So there's a lot of interest in using this as a potential antimicrobial. The problem is that bacteria quickly develop resistance, right? Because it can mutate quickly, so you can mutate key residues that contact the ligands, but they still serve a good model system to study molecular recognition and, in general, structure-activity relationships in RNA. So the third small molecule is WG3, which is inactive. Now, if you look at the kinetics of their dissociation, so the dissociation of the cognate ligand is very slow for this small molecule, which, by the way, was discovered by Merck while they were doing a phenotypic screen. It's faster than the K-off is faster than FMN, and for this inactive compound, the results that were obtained experimentally are kind of inconclusive, right? So one suggestion is that, as I kind of made the argument that kinetics plays an important role, it could be that what's happening is that small molecule binds, but it has a high K-off, right? So the rate of dissociation is high. So we could, in principle, therefore use our selectively scaled MD simulation to study the unbinding of these ligands, and so that's what we did. And so again, movie, you would see demonstration of the fact that we can use our selective scaling approach to actually simulate the unbinding of the small molecules. So at the end, you'll see the small molecule leaving. Now, the utility of this is that we can do contact analysis, right, over a number of replicas. So we could run these simulations, let's say 50 times. And at each time, we can ask what's the probability of the ligand being unbound, right? And you could come up with these kinds of probability traces. So this is a trace you get for FMN, right? So it takes about 50 nanoseconds at the scale value that we use for the simulation for all the contacts to be lost. And so at that stage, the probability of unbinding is 1. So for ribosyl, it's this blue curve here. And for WG3, which is that inactive molecule, you can see this profile suggests that it unbinds rapidly, right? So the hypothesis that emerges from our simulations is the fact that that WG3 is inactive because of the fact that it unbinds rapidly from the FMN, right? And so the system has enough time to actually make an alternative decision when it's trying to regulate between going termination of transcription and whether or not it's going to go ahead and actually execute transcription. So this is a hypothesis and probably needs to be tested, but it kind of highlights how we can potentially use our selectively scaled MD simulation, right? So imagine, again, we're interested in virtual screening. What we would do is screen a large library of compounds, apply a bunch of filters, and let's say at the end have, I don't know, 100 compounds that we're interested in advancing to experimental tests. Before we do that, we can actually run them through this type of simulation pipeline where we predict these profiles and focus on the ones that have the kind of kinetics that we're interested in. In this case, we'll probably focus on the compounds that have a profile that looks similar to FMN, where the unbinding is delayed relative to the other compounds. Now, this sounds fine, but the problem is that these simulations still take for each compound, it still takes about 2 weeks, right, to actually execute. So one of the things we could imagine doing is actually train machine learning models that can reproduce the kinetics and thermodynamics you get from the simulation so that you can make these predictions much faster, right? And so that's one of the directions that we're taking. And with that, thank you.
In the time, maybe we should have one question. Is there one?
Okay.
Thank you, Greg.
Thanks.